Alright, so in this video we are going to finish up the algorithms for rotations. In particular, we're going to finish up the details of right rotate and then also add in what left rotate looks like. So right rotate is the operation that you perform on left-leaning trees like this one. The basic idea is you lift up the L node and you push down the N node and then you rewire. The rewiring isn't much, so L remains connected to A and N remains connected to C, and then you update 3 pointers. L now points to N now points to B, and the parent of N now points to L instead. So it's just a matter of updating these 3 pointers. There is a similar operation called left rotate that you perform on right-leaning trees, and it's very similar. The difference is that we now use the node R instead of L. Because it's the right of the node that it broke at instead of the left. But same idea, you lift R up and you bring N down. And so when you do that, R remains linked to C, N remains linked to A, but then you rewire R and then N to B, and then the parent of N goes to R now. Really exactly the same algorithm, but just completely mirrored. So what we're going to do is go through the right rotate algorithm again and finish it up. We still have a couple details that we haven't filled in for it. And then we'll do a final comparison with right rotate and left rotate with the full algorithm. So the first step of the right rotate algorithm, and we went over this last time, is to label the components. It's really important to use good variable names here because it makes the algorithm much easier to write. This is a very visual algorithm, like you really can't do it without this picture. Anytime I perform right rotate, you know, on a thing, I need to have this picture in front of me. So when the function is called, you have a left-leaning tree, that's a left-leaning subtree that's getting sent in. So N is N in the picture, and then the parent is whatever is coming off of N. So it's N's parent. So it could be on the left or the right of N. So the parent is the parent of N. So those are coming in. So step 1 is to just label all the components. Then you perform the rotation. Then you have to, and performing the rotation is actually just updating 2 pointers. Then you update the parent so that it has the right link, and then you need to update both N's height and L's height. So that's the full algorithm. So we've talked about most of this, but not all of it. So let's look at it in more detail. Step 1 is to label the components. We actually need to label all the components now because we'll need them to update the heights. So we already have N that's passed in, so we need to update the rest. So we need to update L, A, B, and C. And those you can all find from just the picture. So L is N's left, A is L's left, B is L's right, and C is N's right. Then you perform the rotation. So rotating it is just a matter of updating the 2 pointers. So the first one is to update L's right to point to N. So that makes this connection. And then the second one is update N's left to point to B, which is this connection. So that performs the bulk of the rotation. After that, you just need to update the parent. Updating the parent is just a matter of figuring out whether it should go on the parent's left or right, but there is one edge case. So the case is that if it broke at the root node, then there is no parent, so the parent will be null, and so instead you just need to update the root to point to L. Otherwise, you just need to determine whether to put it on the parent's left or right. So last time I showed you how you can check if, by comparing the parent's key with L's key, This is another way to do it, which is if parents left is pointing to n, meaning that the parent was here, then you'll just put L's on its left. Otherwise, if the parent's right is pointing to n, then you'd put it on its right. So that's another way to do it, is just to compare the actual address locations. So that gets the parent linked up correctly. So now we need to update the height. So let's look at what the height update looks like. So updating the heights is we need to update n's height and we need to update l's height. So to update n's height, we need to know B and C's height, and to update L's height, we need to know A's height. So we're just going to go through and calculate A, B, and C's height. As you can see, this is like repeated code. We also used it in the algorithm for insert earlier in the other part of the insert algorithm in order to walk back up and the tree and update the heights as well. Because you have this edge case where if it's a leaf, then it's not going to have a height, so it has to be checked and then set to -1. So we'll talk about how to fix this in a second, but then once you have A, B, and C's height, then you'll just update the same way. So n's height is the max of B and C plus 1, and then L's height is the max of A and N plus 1. So because of this repeated code, this is a good example of writing a nice helper function. So if you pass in a node into this get height function, it will determine whether it should be -1 or its height. And if you do that, you can take that long chunk of code and rewrite it in just 2 lines where you call get height, for each node that you need to find the height from. And you can then use it throughout your whole program. Anytime you need to calculate the height, it will generally work for catching that edge case of a null pointer. So that is right rotate. Here's a summary of right rotate and what we just did, and then the analogous left rotate, which is, as you can see, a very similar algorithm with just a slight mirroring effect. All right, so that is a summary of how to complete right rotate and left rotate. And so we're going to continue to finish up the insert function and what it takes to insert into an AVL tree in the next couple of videos.